you done? Oh, still doing? Okay, we can slowly start, but if you still couldn't finish it, you can keep continue. So I actually saw some of your ideas in discussion. That was very impressive. It was very great. Most of you guys were thinking great about application of this probability and especially estimation and prediction in robotics, in sensing, sensor fusion, in gambling. I saw some of you guys interested in gambling. That was also impressive. About signal processing, like radio frequency signals, and self-driving car, drone control. That's actually great way to think about application of this course. It was my purpose to show you how you can use this course. However, this course is a kind of math, but I tried to connect it to application, to show their applications, to help you to understand them easier. You know, is generally when I wanted to teach this course, actually, they sent me previous slides from other professors, and when I saw it, I thought, I can't teach this course because it's all math, and my major is not math. But they said, that's OK. Whatever you want, you can change it. And but right now, I'm happy that you probably could you got what I wanted to transfer in terms of teaching. I think you got the idea, and that's enough. But still is starting. You know, those applications that you mentioned, you can't implement them right away. I just show you the math behind a little bit. But in other courses, probably you're going to go and deeper see them. Like next semester, I have a class, Sensing and Processing for Robotics. If you have that course, I'm going to teach some of application of this you know, theoretical part that you learn in this class, in that application, in that you know, course that is more hand-on project and lots of applications. Yeah, I also saw some great works, like one student's talking about the quantum mechanics. That's actually impressive. That's very good. And yeah, quantum computing is all based on probability. Even the state is all you know, probability. It's a wave function. And that's very impressive. Actually, that's the future, I think, the future of computers. As I mentioned, everything in this world is probabilistic or stochastic. So the computers need to be also friendly with the stochastic processes, like how quantum computing works. Quantum computing is all based on probability. And yeah, that was good discussion. Still, you have time till Friday to complete that and try to respond other ideas. If you think something nice there, you can talk that. And it was actually good idea. Okay, so let's go for rest of the class. Let's see, where is my page? Okay, here. Sorry. Okay, so what we're going to talk today is about, we want to add more dimension to random variable. We talk about random variables and joint random variables, if you have x and y, for example. And last week, we talked about, not last week, actually, this 2 days ago, Tuesday, you learn how you can estimate something, how you can predict something. We show you that you can predict something. You can actually, predict something and then update it. So in these two formula actually are everything. It's showing you how your belief, that's your belief. Mean means the belief. Your belief is changing based on previous belief and new observations that give you new information. And that y minus mu is actually how your measurements changing regarding to previous belief of measurements. And we call that innovation or error sometimes. And also we need this covariance for future. You know what I'm saying? We need this covariance to see our uncertainty because the main thing is our belief, but or updated belief actually. But we want this because it can go forward, and go ahead in time. And this is actually the formula for evolution. What is evolution? Evolution is you had something and you update it to something new based on new environments, measurements, and keep going. This is actually very amazing formula and can answer so many questions. So it's based on predict and update. So you always use that. You predict something and then update it. How update it? With new observations, with new measurements. How you predict it? From previous knowledge, you predict it. Sometimes prediction is just blind estimation, just get mean, average. But how you want to update it, you need to get new measurements. And this is the formula for update. The mu x is prediction. You predict it, and then you update it. So this is the basic of what I wanted to teach and what you learned last class. We also talked about mean square error and minimum mean square error and linear minimum mean square error, and also Gaussian. We talk about these two. Gaussian is also very close to linear. They become actually similar. The formula, the last formula, is similar. But today we want to go another dimension higher. Instead of having just 2 variables, we can have n variables. This is going to give us possibility to model a function of variables, random variables. You know, like a trajectory, or a signal, for example. A signal, when you digitize it, it becomes some numbers. Those numbers are random variables, x1, x2, xn. We're going to talk about that today. And if we get a chance, we might not, talk about whitening, how we can remove correlation. That's called whitening. So whitening is like removing noise. You know, in so many applications you can use that. And whitening is like transforming. And as I mentioned, transforming is not changing probability in a small parts. So you always can transform one random variable to another random variable. What about to transform a group of random variables to another group of random variables that they are not correlated? Is it possible? Yes. It has some linear algebra behind, but you always can use Python or MATLAB for those. Maybe you need computing eigenvalue, eigenvectors, or those stuff. That's like mathematically, some of them are expensive in terms of computation, but computer can do that for us. Don't worry about that. So that's also important. We're going to talk about that in following lectures. Let's go for random vectors. Random vectors is just the vector of random variables. As I mentioned, lots of application. PDF is a joint PDF. Why join? Because x1 and x2 and x3 might be depend on each other, might be correlated. If they are not correlated, we can break them down. We can factorize them if they are not correlated. But most of the time, they are. Compared to the previous topic, we talked about joint random variables for 2. But right now, we want to go for n dimension. And in practice, we see that a lot. As I mentioned, in signal processing, you can sample signal, trajectory, function. Even you can make a continuous function, break that down to multiple random variables. That is actually a random function that later we're going to see that. It's called a process, or a stochastic process, or random process. A process is a function of random variables in time. They are changing in time. That's to become process, random process. We're going to see that next class. We have 2 other topics to cover after this. One is hypothesis testing, is just 1 session. And another part is, the rest is all actually process, random process. We're going to talk about random processes. If we get chance, we can talk about the Gaussian random process. That is amazing. It's like another way of look at artificial intelligence in an explainable way. You know, artificial intelligence sometimes is not explainable. Like when you are using data to find your model, it's not explainable. Mathematically, you can't prove it. You know, that's called, that type of AI is not explainable AI. When you train the model using deep learning, neural network, or any family of neural network, that's not explainable. That's actually weak point of that. because if you go to the bank and bank reject you for getting loan, you might complain, why? But nobody can answer you. They said, AI said, no, we don't have any reason. Because there is no way to find the reasons. There is no explainable things. That's coming all from training and data that's coming, lots of data that just train the model, and input coming in and output going out, and output was rejection. And there is no way to explain it. This kind of AI called not explainable AI, but there is another way of look at AI is explainable. Whatever we are talking about, Bayesian methods or later a Gaussian process is like AI. You can see that. You can predict a function. Because AI is function optimization. You are finding a function. You are optimizing a function. And that can do function optimization as well. Anyway, we're going to see that next week, or end of next week. Yes, that's signal samples. These are multiple random variables, vector of random variables like that. Also, in a simple case, imagine you have a robot that's moving in 3D dimension, or if it's not 3D, even 2D, like a ground robot, X and Y, but you have other things like velocity, acceleration, jerk, and each of them can be X and Y. Also, you can have orientation. So this makes a vector. And this robot position by itself in each point is multiple numbers. Imagine in a trajectory. It makes a set of vectors. So it's going to be good to study this type of random variables. So in this case, probability, because it's continuous, if we consider it continuous, it can be discrete as well, but continuous is nicer to study because it's all mathematically explainable, and you can see the math behind it. So anyway, probability of x in that space when you have a vector is actually the integral of, like n times integral of that function, that PDF. So this is the PDF. So in 2 dimension, it's going to be 2, like if p x I, a I, b I, and I is 1 and 2, This is like A1, B1, A2, B2, f of x, x1, x2, d of x1, d of x2, like that. So this is probability. If you want to find the probability, you need to get integral. And if it's multiple dimension, you need to do this integral multiple times. And this part is everything. Look, PDF is everything. PDF gives you enough information for modeling your system. So if you find this PDF, I can say you have everything to predict whatever you want. So sometimes it's easy to find PDF, sometimes it's complex. So these variables sometimes are dependent. I mean, x1 and x2 sometimes are dependent, sometimes not. If they are not dependent on each other, if they are not dependent, it's easy to find PDF, because PDF in that case can break down, can factorize. This we call it factorization. It can be a product of multiple functions. Those functions are actually just f of x1, f of x2, f of x3, and so forth. So this is the simple case. If the independency exists, so PDF can be factorized. So factorization is very important. Even in Bayesian models, Bayesian methods that we had before, factorization can break down big problem to small pieces. Why this factorization is very important? Because it can save time and makes everything simple. Why? Imagine this is posterior density, P of x given y. When I put, because vectors, we show vectors with bold capital characters, but to show bold things, I need to put them like that. So this is, if we factorize that, like instead of f, we have, for example, probability of x1, y1, or probability of x2, y2, probability of x3, y3, something like that. If you factorize them, or maybe in general, when I do product, doesn't need to write everything. So maybe just write this. If we can find this posterior density factor of something like that, the rest is easy, because when you want to do maximization or minimization, because you need to. If you want to find x, you need to maximize this and find the x that maximize this. Maybe I need to tell like that. I need to find x that maximize this probability, because this is probability of x given y. It's a conditional probability, and we want to maximize this and find x. So if it's like a product, because in maximization or minimization, log is not changing anything. So log of this, actually, log of mean of this is equal to mean of this. So log is not change anything, but log affect this multiplication dramatically, because if you get log, this product gonna get summation, isn't it? Log of x, y is log of x plus log of y. You have that, and this makes everything linear. This is not linear because product, but it becomes linear addition. And you can solve it in very well-known methods, like Gaussian Newton methods. We might see them later. OK, anyway, that's a very good point to can factorize things, but not always possible. But we sometimes can approximate these factors. Sometimes we can just approximate them. I mean, we do some assumption and make the life easier. Let's clean this up. So that's when we have independency between random variables. We can factorize that. Let's have example. Like, for example, imagine we have two random variables, x and y, and they are both Gaussian and independent. Since they are independent, and they ask us what is the PDF, joint PDF, of course. So in this case, so in general, PDF of Gaussian random variable is like that. Do you remember f of x is equal to 1 over the square root of 2p sigma square exponential minus x minus mu square to sigma square. So this is the general form of normal PDF of normal variable, normal, or Gaussian. Gaussian distribution. This is the normal PDF for one random variable. If you have just one random variable, x is like that. We're going to see that if we go for vectors. But this is Gaussian PDF. But we have these two. And because they are independent, the joint PDF going to multiply these two. So if we find the product of these two, it means product of these. Sigma is, here is 1. Here is also 1. And mu is 0 and 2. If we multiply them together, this exponent part get add together. So the result going to be like that. OK, that's how we can find a PDF when random variables are independent. But finding PDF is not easy. In this case, was easy because of independency. Independency is like constraint that we consider. It's not always independent. Any question about this? Good. Let's find the mean and covariance. Imagine we have a vector of random variable, and we want to find mean. In one random variable, mu of x is equal to e of x. X is just one random variable. That is equal to integral of x f of x. F is PDF, d of x. So we know that for one random variable. For a vector of random variable is also the same. But for vectors, x is a vector, is a bold capital. And as you can see, you can get integral the same way. And it becomes, again, a vector. So the vector, the mean of a vector of random variable is also a vector. That each element of that vector is actually mean of that specific random variable, like mu of x1, mu of x2, and mu of xn. OK, in random vector is like a cloud of random variables. You can imagine a random vector as a cloud of random numbers in 2 dimensions, for example. And mean is a centroid of that. So the mean is a centroid. If you want to visualize it, it's like a centroid here. This is called mu of x. And this x is the vector. All of those points are those vectors. And this mean is just one of the points that's showing centroid of that mass or cloud. If you want to visualize, yeah, here, the center of the mass of the probability cloud. That's called the mean. For example, you have a vector of position and velocity. And the mean of that is the mean of positions and mean of velocity. You just need to get mean of velocities and add, if there is multiple of them, add them together and divide by number of them to find the mean of each one. So the mean is simple. It's like normal random variable. Nothing changed. What about covariance? Covariance is also, we know the formula is for one variable. We call that sigma square is expected value of x minus mu x square. OK? So we knew that for one variable. But if we go for a vector, this square changing to matrix form becomes like a dot product. That's a product of these two matrices. X is vector, mu is a vector, and that is also a vector, but you transpose it, you can multiply them together. What is the result? Is it a vector or matrix or number? You know, if you multiply this by this, A, B, C, D, this is going to be a number, like K. If you multiply this by this is going to be a matrix. And so that's also, the result of that is a matrix. So this matrix is a covariance matrix. So let's clean this up. And this matrix showing covarying variables. How these variables, we have n variables. How they are covarying, how they are varying regarding each other. So we had that for 2, that was variance and covariance. Here we have the same as well. But this covariance is for each variable separately. Variance of x, x1, covariance of x1, x2, covariance of x1, x3, x1, xn. And here as well. Variance of x1, variance of x2, x1, and xn, x1, and the rest. We just add dimension. So this is the covariance. So the covariance is kind of showing how these variables covarying respect to each other. Like how x1 and x2 change regarding to each other, how x2, x3, and all of them. And this matrix explains everything. This matrix actually explains everything for us. Covariance is so important. In this covariance, covariance matrix, we have, first of all, is a symmetric, because covariance of x1, x2 is equal to covariance of x2, x1. So this is first things. So this is, there is symmetric. So it means this is a diagonal. And this is the off diagonal showing covariance. And diagonal is variance. And off diagonal the covariance. And this is another important part about a covariance, that always is positive semi-definite. In some applications, we need to know that. So if it's positive semi-definite, means the eigenvalues are always positive. We're going to see eigenvalues, what this eigenvalue means. So the covariance shows lots of information. It's showing how you are varying regarding each other. And in one dimension, the covariance was showing how you are varying around the mean. And in one dimension, the covariance, actually covariance showing that picture. And in 2 dimensions, showing like ellipse. And in 3 dimensions, showing, again, ellipsoid in a 3D. And when you go 4 dimension, become hyper ellipsoid and go forth. You can imagine more than 3. But this is how you can visualize covariance. So we call it geometric meaning of covariance. So covariance showing some visualization of random variables. How we can visualize it, you just need to write the covariance in this form. And this is like quadratic form of covariance. So this is like the formula for circle. For example, formula for circle is something like that. If you have a x, imagine x has 2 points, x and y, but we just have a vector of x. And the center of that circle is c of x, for example. This is the formula for circle. But the circle, the sigma is all diagonal. Off diagonal is all 0, because there is no correlation. That's why it becomes circle. So in this is for circle, this becomes circle. But if you have correlation, this becomes ellipse in 2 dimensions. Anyway, I just wanted to mention this and how this is coming. So this is how you are visualizing covariance. Some information about this. You need to know, for example, in this ellipse, the direction of ellipse is showing how is like a stretch. The direction of ellipse coming from eigenvectors, and like this and this showing the direction of ellipse, and eigenvalues showing the length of those axes. How we can find that eigenvalue and eigenvectors? There is so many, like in linear algebra, you can find that because you know eigenvalue and eigenvectors are principal components of the a vector, like a matrix. Okay, a matrix. We are talking about eigenvalue and eigenvector of covariance matrix. We are talking about this matrix, and this matrix is a symmetric matrix, and that's why we can play with that very easy. In linear algebra, when a matrix is symmetric, is easier to factorize it, it's easier to work with that, it's easier to invert that. Inversing is a very hard part in actually linear algebra. And we have here invert. So that's why, because sigma is not a normal matrix, is a symmetric matrix, it makes life easier. Anyway, computing eigenvalue and eigenvector. What is eigenvalue and eigenvector is this. If you have matrix A, eigenvalue and eigenvector of A is coming from this formula, as you know. Do you know that anyway? Do you know eigenvalue and eigenvectors in other courses? You had that before. But in this class, we're not supposed to compute them. Of course, there is some tools to compute them in MATLAB or Python, whatever. But that's the formula to find them. This is the matrix A, and V is eigenvalue. And this, the lambda is eigenvalue, and this is eigenvector, sorry. Eigenvector, eigenvalue. So eigenvalue is showing the size of those vectors, and eigenvector showing the vector of this ellipse in 2 dimensions. In 3 dimensions, become ellipsoid. So it gives you lots of information. For example, if this is a robot, and that's showing the position of the robot and uncertainty around the robot, with computing eigenvalue and eigenvector, you can see which direction is robot moving. The longest eigenvector showing that. And direction is also exists. Anyway, this is some information about this formula, and that's coming all from covariance matrix. This sigma is everything. So in robotics and estimation, covariance represent the confidence. And so what that means, a smaller covariance means higher certainty. And how we make covariance smaller? With new observations. Do you remember anytime we get new observation, the covariance gets smaller and smaller? And it means better prediction. So update it. Let's have example. Let I clean this up. So imagine you have a mean 0, and you have a sigma. It's just 2-dimension, x and y. So the sigma is 2 by 2 matrix. If we find, actually, this is Python code. I didn't show the Python, but it's very easy Python code. You can write it, or in MATLAB as well. If you draw that, if you plot that, these arrows showing eigenvectors and eigenvalues, and this blue ellipse is the shape of that formula. How you can do that? So x is changing, mu is given, sigma is given, and you can just draw that using plot in Python, and it's going to draw that like this. You can play with that a lot. So the shape of the covariance is an ellipse of uncertainty around mean. Any question about this? So this is just 2-dimension like before. We didn't go more than 2. It still is 2. But the point that we are showing in that formula is how we're showing ellipsoid or ellipse representing covariance. So how we can do that with that formula? You put covariance over the covariance is kind of normalize it. Normalize that square. That's a square, actually. X minus mu transpose and x minus mu. When multiply them, we are making, a square of that. Okay, so let's see what I check to see everything I mentioned here. Okay, yeah, I think we're done here. Let's go for another example. So this example is still we are in 2, but it can be 3. We're going to make this 3 in next slide. We have a temperature in different hours. You know, for example, you are one of the application of this course is actually for predicting weather. For weather you can use that. In this example, we are measuring some temperature, Fahrenheit, in different hours, like x1 is in 6 a.m., x2 is 12 p.m. Are they random variables? Yes, they are random variables because coming from sensors, and it's continuous random variables because it's temperature. And we put them together, join them together in a vector. This is a vector, capital X and bold X. And the mean is given. We have the mean. How we have the mean, we did it in many days before. We add them together and divide by the numbers, and we have the mean. And we have also covariance. Covariance is also can get computed based on the previous information. You can find covariance. The formula is given. And you can find that. And what we want now, we want to find joint PDF. Okay, can we find joint PDF? Okay, about joint PDF, before that, we need to know another dimension of Gaussian distribution. Okay, first of all, I didn't mention in that example, but we are imagining that these values, these random variables, are Gaussian. Actually, they are Gaussian. Temperature is Gaussian because the next temperature is very close to the previous. They are smooth. Temperature changing is smooth. I don't know. In Houghton is not. Probably it's changing one day and suddenly get so cold, so warm. But normally is smooth. Even if it's changing so hard, it still is smoothly changing. So it's Gaussian. Gaussian means a smoothness. Smoothness, yes. A smoothness, sorry, a smoothness. So sometimes we call it a smooth factor. Every time we want to say, okay, this is Gaussian, so it has a smooth, it's changing smoothly. The Gaussian is very good for so many phenomena that change smoothly. Like for example, for autonomous systems, most of the time, the previous state and the next state are very close to each other, change a little bit. They're not changing a lot. And if change a lot, that's not Gaussian. When we call it Gaussian, it means they are changing a little bit, smoothly. So anyway, in this example, we are imagining, I forgot to mention, that this x1 and x2 are Gaussian, and they make a joint Gaussian. We are going from joint two variables to n variables of Gaussian. We call it multivariate Gaussian PDF. Multivariate, it means a Gaussian PDF that is n variables. Lots of variables. So how we can write that? This part is just, in Gaussian, you had this, remember? In one dimension, you had exp minus x minus mu square to sigma 2. This is exactly the same. 1 over 2 is there. Sigma square become capital sigma in in vector random variables. So, and this is going to come up. That's why we have invert of that, and a square coming from that. But in a matrix form, to show this, we need to use that form that is quadratic form. This quadratic form is actually that shape of ellipsoid that I talked about in last slide. That's a quadratic form that's showing everything in top of this exponential family. And this part is also similar. In one variable, it was 1 over the square root of 2 pi sigma square. But in multivariate Gaussian, still you have that 2 pi, but instead of 1 over 2, because the square is power 1 over 2, we have n multiply 1 over 2, or n over 2. And the sigma square, again, becomes sigma, like a big sigma. But we have determinant over there. We have determinant over there. That's the formula that we need to use when we have Gaussian random variables. We have multiple Gaussian random variables. That's become the formula. So x is a random vector, mu is a mean, and sigma is a covariance, and that is a determinant of covariance. Okay? So based on having that, we want to find this PDF. But here is just two variables. It's simple. And n is 2. So the formula changing like that. Because n is 2. 2 over 2 is 1. So it's 2 pi. And I didn't compute the rest. You just need to put those matrices and find a function. You have still x. But mu, you're going to put that mu there and sigma as well and find the inverse of that. And that's the result. So this is how Gaussian variables jointly become a new Gaussian using this multivariate Gaussian PDF. Let's see if I mention everything here. Another interesting part that we can say about this quadratic form, this quadratic form is kind of distance of x to mean as well. But this is not a normal distance. This is distance of x to mean. Because you know in one dimension, if we write x minus mu square, so x is, for example, this point, and mu is this point. So this is showing the distance between x and y. This is, we call it Euclidean distance. But this is also distance. But in this distance, we normalize that with sigma. We normalize that with sigma. We are getting distance from distribution. Is much precise, more precise than that. In here, we don't care if that point has some uncertainty. But in that one, we also considered uncertainty. Interesting, yeah? So distance changing when you have uncertainty. That kind of distance called Mahal distance. I just need a space to write, maybe make a space here. This is called Mahal distance. So x minus mu transpose sigma inverse x minus mu. This is called distance, d Mahal distance of x. However, this is squared. You need to make a square root of that. That's called I can't pronounce it. Mahalanobis distance is the name of the guy. Mahalanobis distance is an Indian scientist that in 19th century, around that, is also called normalized distance and Mahal distance. If you are working with robotic, if you want to find the distance between robot and an obstacle, if you use that, fail. Because in robotic, you have uncertainty, and that uncertainty coming as a covariance. And this covariance need to go in the distance, this distance called Mahal distance. You need to use this formula. Very important. Have you had that before in your other courses? You had class with me. I think I told that. Yeah. But you didn't, no? Nobody? Yeah, that's good. You learned something very, very good. And it's going to help you a lot. Because distance, so many times you measure distance, but it is uncertain. You need to put uncertainty inside that. Where is this uncertainty? Here. That's why we call it normalized distance. We normalize it. We normalize it. So, for example, if the uncertainty is too much, this distance might be far, even though they are close. You know what I'm saying? It's changing your imagination from normal distance, you know? You know what, like what? When you are watching something, your eyes is like 10 from 10. Is it from 10 or 20, 20 from 20, for example, you can see everything very precise. So the distance that your eyes can measure, it's more precise. And imagine you put, I don't know, cloudy lens in front of your eyes. And you make lots of uncertainty here. You can't recognize the distance properly. This is exactly same. So this is called mahal distance or Mahalanobis distance. Is name of the amazing Indian scientist. His name is Prasanta Mahalanobis in 1930. That he found that, and that's amazing improvement in finding distance in uncertainty. Okay, so that's good. Let's go see what else we have. We have also transformation. Transforming is amazing, especially for removing noise. I mentioned at the beginning of the class, sometimes you can transform a random variable that is correlated to somewhere else that remove correlation. That helps a lot. Transformation happening can be linear transformation, like before, but here, x and y are vectors. A is a matrix. A is a matrix, B is a vector too. So in this case, mean is just changing, like similar. Remember, we had that before. We said, okay, if we transfer with AX plus B, mu of y is going to be A mu of x plus B. This is exactly the same, just in a matrix form. What about covariance? Covariance also was the same. We said covariance, in that case, variance of y is a square variance of, it is a square, variance of x. Do you remember that? This is exactly the same. This is the covariance as well. A square. But in matrix form, a square is quadratic form. Sigma is a square matrix. The dimension of that is equal to the dimension of vector. You can multiply them together. And when we multiply these together, again, the result is another matrix. Imagine A is here and A transpose is here. And this become another matrix, but transposed matrix. So B, also called shift vector, so because it's shifting the mean. So for example, the cloud was here. You are shifting that with B to another cloud, and this cloud is changing. For example, here was ellipse, here becomes circle, or vice versa. Or become any other shape that you are imagining, you know, based on this function. But this function, if it's linear, is like that, mostly moving in a linear way. And what about A? A is like rotate and scale. Rotate and scale. Any question about that? So transportation is important in a way that you can sometimes remove noise, for example. That's good job. Before going to whitening and removing noise, or maybe next class, I'm just going to solve this and rest for next class. Linear transformation. Do you remember I had example of temperature? We measure temperature in different times. Here we add another vector to that, another dimension to that. We are measuring temperature in Fahrenheit in different hours. And we got this mu and covariance. We have covariance and mu, 50, 62, 58 Fahrenheit, and covariance is changing like that. As you can see, there is, off the diagonal, that's showing covariance, but as you can see, the diagonal is the same. Like it's changing x and x1, x2, and x3. The variance of them are the same. What we want to do, we want to change from Fahrenheit to Celsius. Wow. We can do that. We just need to transform this. Because random variable is the same. We are not changing the outcome. Everything is the same. It's the temperature. We just want to watch that differently. Linearly, we can transform that from one space to another space. In this space, transformation happening like that. First, we need to find these matrices. Because this matrix, everything becomes matrix. So here, we find that transformation matrix. We find A and B. So because it's just 5/9, we add that by the matrix, I matrix, I3, means 3 by 3. And B is also a vector of 3 numbers. And we just need to put in the formula that we had for computing the new mean, because new mean is going to just transfer easily the previous mean plus B, plus this A, that this is the number here. However, it's not just a number, it's a matrix, but because it's I matrix, its multiplication is very easy, plus this, and the result going to be that. And for covariance also, we square this A and multiply with the previous covariance to find a new covariance. So that's how we are transferring from one space to another space. And here we see application. We are going from Fahrenheit to Celsius. OK, next time we are talking about whitening and see how this transformation can help for amazing things. You have a signal with noise, and we can whiten that. We can make it, white or without noise. If there is, for example, correlation, we remove that correlation. It's possible to do that. OK, any questions? Perfect. So see you next week then.